Hi, I'm Claudia Damaris Kaban, and in this video I will walk through my Jupyter notebook for topic 11, Gradient Descent, a foundational optimization algorithm used to minimize loss function in machine learning and statistics. I will demonstrate how the algorithm works, when it fails, as well as mention and demonstrate one of the possible improvements. I define my quadratic loss function, f of x comma y equals 1/2 times x squared plus 5y squared, with the gradient is equal to x and 5y. This function has two eigenvalues, lambda 1 is 1 and lambda 2 is 5. So the condition number is k equals to 5. And for convergence, the learning rate must satisfy less than 0.4, which is 2 over the eigenvalue. And this is the 3D loss surface, and this is a smooth convex bowl with a single global minimum of 0.0. So I test three learning rates. The first one is 0.18, which is closer to the stable rate at 0.40, and the second one is 0.03, lower than the stable learning rates, and it will show that the path will be slower. And the third one is 0.60, which is bigger than the stable learning rates, and we will see that it will diverges. So in the output, it shows that the final loss for the first learning rates is nearly 0. And however, the final loss for the second learning rate is not exactly zero and still far away from the minimum. And the final loss for the third one, which is which we intentionally set to be bigger than the stable one, is possibly equals to 1 billion. In here, I plot all three paths on the contour map of the loss function. With the orange one is the good one. It will finally converges and with a visible zigzag in the beginning. And the green one is the slow one with learning rate of 0.03, and it crawls slowly, way slower than the 0.18 learning rates. Next, I will explain the gradient descent with learning rate of 0.60, represented by the purple line. And for visibility, I actually pin this contour map onto -3 and 3, so that's the maximum oscillates that we can see here, but in reality this oscillates over 3 and -3. Here we can see the animation of the best learning rate, which is 0.18, and we can see that it finally reached the minimum point, within 80 steps. So this is the second part of my demo, which I will compare basic gradient descent and an improvement of gradient descent itself. There are actually several methods to improve gradient descent, such as momentum, adaptive step size, and line search. Today I will use decay learning rate, which is a simple way to improve gradient descent. Instead of using the same step size for every iteration, we start with a larger learning rate and slowly decrease it using the formula learning rate 0 times gamma to the power of t. This makes the training fast at the beginning and more stable when it gets close to the minimum. So in this section, I will demonstrate gradient descent on a two-dimensional function with two approaches. The first one is using a constant learning rate, and the other one is using decay learning rate. The plots you will see in the next section is the optimization path of the contour surface, the loss over time, and how the learning rate will change during the training. The function that we are trying to minimize is f of x comma y equals 1/2 times x squared plus 20y squared. Keep in mind that this function is a condition beforehand. Now, let's take a look closer to the first figure. This is the function basically. And then to the first figure, We can see that the blue one is the constant gradient descent, where the green one is the uh, learning using decayed learning rate. And with the blue one, the constant learning rate is 0.06, whereas the green one with decayed learning rate, uh, at first it is 0.095 and then decays by a factor of 0.99 each iteration. So we can see that from the green curve, in the beginning of the path it is faster movement. It has a fast movement, but as the algorithm approaches the minimum, the learning rate becomes smaller and the path is also smoother with fewer oscillations. And from this figure we can figure out that there is a proof with the benefit of the decay is that both of them are reaching the minimum, but the decay learning rate finishes more smoothly and efficiently. And I believe if our function is not actually conditioned beforehand, decay learning will help minimize the loss function. So these two graphs are showing how the learning rate changes during training. So again, the blue one is the constant learning rate, and the green one is the one with the decay learning rate. Maybe we kind of like notice that the constant learning rate is closer to the minimum. However, as I mentioned before, because we are testing it on a condition function beforehand, so that's the reason why the formula shows things like this. However, if we pay attention more, we can see that the decay learning rate is actually more smoother, and on top of that we can see that it gradually decreases the oscillation towards the minimum rate. Together, these two graphs shows that learning rate decay gives the best of both worlds, which is fast progress at the start and smooth convergence at the end. So as a statistician in a government organization, I deal with models using large, noisy, or high-dimensional datasets, such as household and economic indicators. And they can be computationally hard to analyze. And in this case, gradient descent actually provides a scalable and flexible, as well as memory efficient optimization framework that works even with when the matrix inversion is not actually possible. Thank you so much for your time. Have a good day.